Modern physics relies on two pillars to explain reality, one for the micro-universe of subatomic particles and one for the macro-universe of galaxies. The standard model of particle physics is a theoretical fortress that has survived decades of rigorous laboratory testing. Its macroscopic equivalent is the lambda CDM model. Lambda cold dark matter is the standard framework that describes the large-scale structure and expansion of the universe. While the particle physics model remains pristine against experiments, lambda CDM currently faces a severe statistical crisis. New data exclusions are hitting significance levels as high as 4.2 sigma. In statistics, a 4.2 sigma result suggests only a 1 in 30,000 chance that the predictions of the standard model are correct. Why does one standard model easily absorb anomalies, while the other threatens to collapse entirely under new data? This divergence results from the internal architecture of these models and the physical limits of observation. Cosmology operates under a strict epistemological limit. We only have one universe to observe. This creates the n=1 problem. An n=1 sample size means we have exactly one instance to study, making it impossible to rerun the Big Bang under different initial conditions. Standard laboratory sciences do not share this handicap, as researchers can isolate, manipulate, and retest single variables in controlled environments. To compensate for the inability to run multiple experiments, cosmologists must rely on global statistical fits across entirely different physical epochs. They stitch together massive, disparate datasets, combining ancient light from the cosmic microwave background, baryon acoustic oscillations, and local supernovae. The cosmic microwave background is the residual thermal radiation from the Big Bang, while baryon acoustic oscillations are periodic ripples in the density of visible matter. For lambda CDM to work, these radically different data sets from separated points in time must perfectly align with the same theoretical curve. Operating within an n=1 reality makes any holistic model fragile. Its survival depends entirely on every localized piece of data remaining perfectly aligned. The standard model of particle physics avoids this fragility through its specific theoretical architecture. Its defining characteristic is modularity. It describes localized interactions and individual fields that can be completely isolated from one another. Physicists test this modularity through high-frequency, repeatable experiments. The physical scale of these tests relies on brute force repetition. By colliding billions of particles, researchers generate isolated statistical distributions, allowing them to probe specific quantum fields without needing to factor in the entire history of the universe. We can see the strength of this architecture in a historical anomaly, the discovery that neutrinos have mass. Because the standard model is modular, physicists did not have to throw out their entire theoretical framework to account for this new data. Instead, they patched the anomaly. By modifying a single mathematical parameter, they updated the specific equations governing the neutrino. Modifying this single parameter slightly shifted a local equation, but it left the rest of the standard model, from quarks to bosons, completely untouched. Modularity breeds theoretical resilience. When new data arrives, the particle physics model bends to absorb it. The architecture of the lambda CDM model lacks this modular grid. Lambda CDM is monolithic. It models the entire universe as a singular, heavily coupled entity, rather than a set of independent interactions. The model rests on a strict 6-parameter mathematical foundation, which includes values for dark energy, denoted by the Greek letter lambda, and cold dark matter. This diagram maps the evolution of the universe from a dense quantum fluctuation on the left to an accelerating expansion on the right, visualizing the vast span of time and space these 6 parameters must govern. In the early universe, we see the formation of the primordial plasma and the initial acoustic peaks. The parameter for cold dark matter gravitationally dictates exactly how these ancient structures form and clump together. Shifting to the modern era, a completely different parameter, dark energy, dominates the current accelerating rate of expansion. The fatal flaw in this monolithic structure is coupling. These 6 parameters are mathematically entangled across time. You cannot adjust the density of cold dark matter in the ancient universe without altering the mathematical output for the acceleration curve of the modern universe. Unlike the neutrino example in particle physics, cosmology offers no isolated modules to safely patch. The assumptions about the universe's geometry, its expansion rate, and its matter distribution are so intertwined that changing a single value rewrites them all. Monolithic models face a binary reality. Because they must model everything all at once, they either fit the data or they fail. That failure is happening now, initiated by a sudden influx of high-precision cosmological data. This data originates from a completely new generation of highly advanced space instrumentation. The Dark Energy Spectroscopic Instrument recently mapped the exact spatial locations of 15 million galaxies. The Dark Energy Spectroscopic Instrument is a specialized telescope attachment designed to measure the expansion history of the universe. Researchers combined this massive dataset with pre-existing Pantheon Plus supernovae data to test the established lambda CDM predictions. The baseline expectation was clear. If lambda CDM is correct, the combined data should map perfectly to a constant, unchanging line representing dark energy. This chart plots a perfectly flat line representing constant dark energy, but new data points curve distinctly downward, away from it. This carries immense statistical weight, a 4 sigma tension indicating dark energy is dynamically evolving over time. This specific deviation breaks the lambda in lambda CDM. The data forces a choice. Either multiple world-class datasets are simultaneously wrong, or the monolithic model is broken. Deleting individual datasets, like removing the supernovae data entirely, does not eliminate the tension. The anomaly persists across independent metrics. It is statistically improbable to assume that all of these different instruments and datasets are conspiring to be wrong in the exact same way. New theoretical frameworks are waiting to replace lambda CDM, specifically modified gravity models like F of R gravity. F of R gravity is a family of theories that modify Einstein's general relativity by altering how the curvature of spacetime responds to mass and energy. These alternative models provide superior mathematical fits to the new curving data of evolving dark energy. Because lambda CDM is monolithic, cosmologists cannot simply slide an evolving dark energy module into the old framework. The core equations of expansion must be entirely rewritten. The statistical success of lambda CDM lasted decades, but in an n=1 universe, a persistent anomaly forces the total reconstruction of the expanding cosmos.